So now we're going to talk about how we can find the derivative and working with derivatives in more of a functional sense instead of graphical. So we're going to start by looking at a graph, but we're going to talk about kind of like the easier ways that we can find derivatives. So if we have a constant function, what is the derivative going to be? So for example, if I have f of x equals 3, if I were to graph that, that's just the line y equals 3, right? Based off of what we did in the previous class, if I wanted to find the derivative of this or graph the derivative, I look to see where the slope is 0, right? Well, the slope is 0 at every point on this line. So if I wanted to graph the derivative of this, it would just be the line y equals 0. Pretend this is a nice straight line. It's not, but pretend it is. Okay, so the red line would be my derivative. So f prime of x is equal to 0, right? The slope of that line is 0. So that is what my derivative is. So if you use the definition of the derivative, like the limit that we did in the previous class, and you plugged in everything, right, it solves it for you. But here's the main thing we want to focus on, right? The derivative, so d over dx, that's just a way of writing the derivative. So the derivative of c is equal to 0. So c is a constant. So if I have the derivative of any number, 5, 10, 12 million, right? The derivative of that would equal 0, because if you were to graph it, the slope of a constant is always 0. What is the derivative of f of x equals x? So again, I'm just going to draw a really bad graph here. So f of x equals x is just the line y equals x. Pretend that that is actually correct. Okay. So if I wanted to find the slope at a point on this line, right, any point, it's going to have a constant slope, and we can see that the slope of this line is 1. So if I were to graph the derivative of this, it would, pretend that's straight. Whoops, it's not straight, but pretend. Okay, that's going to be our derivative because it has a constant slope of 1. So it's above the x-axis because it's positive. So we could say that f prime of x is equal to 1, right? So that kind of makes sense by looking at the graph. So now we're going to get into the power rule. Okay, so the power rule you might have already seen. It is the very easy type of way to find derivatives that meet certain criteria. So why do we use the power rule and why does it work? I am just going to show you. We're not going to go through it. So if you're curious about how this works and why it works, here it is. So you can see it. I'm going to go through it very, very quickly. So basically, if we use the limit definition of the derivative, and we found the derivative of x squared, x cubed, x to the fourth, and we just kept going and kept going. Again, here I'm just going to show it to you, but we're not going to really do anything. So using the limit definition of the derivative, which is pretty annoying to use, if we kept using it, when I take the derivative of x squared and I simplify everything, I get 2x. When I take the derivative of x cubed and I simplify everything, I get 3x squared. When I take the derivative of x to the fourth and I simplify everything, I get 4x to the third. So if I had the derivative of like x to the n, like any number, it would follow the same pattern. And that brings us to the power rule. Okay, so the power rule is saying if you take the derivative of x to any exponent, that's a number, you take the exponent, multiply it in front, and subtract 1 from the exponent. Okay, so we're going to look at a couple of examples. So if my function is f of x equals x to the sixth, and I want to find the derivative using the power rule, my exponent is 6, so I'm going to put it in front, and then I'm going to take my exponent, and I'm going to subtract 1. So this would be 6x to the fifth. Okay, so those of you that already know this, great. If you don't, you can write it the way I'm writing it for now to understand, but basically we're not going to write the 6 minus 1. We're always just going to write it as 5. The power rule works when you have a number to an exponent. So if I look at the second example, I have a fraction. I have 1 over x squared, and that doesn't look like the power rule, and it's not set up to use it easily. So we can rewrite things as long as we don't change them mathematically. We can rewrite them to make it look like we can use the power rule. So if you remember, exponents in the denominator means that you had a negative exponent in the top. So I'm going to rewrite this y function, and instead of 1 over x squared, I'm going to call it x to the negative 2. Okay, so by just rewriting it, it's now set up like the power rule. So if I wanted to find the derivative, y prime, I'm going to take the exponent, multiply it in front, so negative 2x, and then I have the exponent of negative 2, and I'm going to subtract 1 from that. So I end up with negative 2, x to the negative 3. Okay, and let's look at this one here. So again, not set up great for the power rule, but if you remember your rational exponents, we can rewrite it. So a radical like this can be rewritten as x to the 2/3. So now that we have it written as x to a power, we can find the derivative using the power rule. So I'm going to take the exponent, which is 2/3, that goes in front, and then I have x to the 2/3 minus 1. But remember, 1 is really 3/3, so just to make it a little bit easier. So we end up with a derivative, g prime of x is equal to 2/3 x to the negative 1/3. Oops. So the power rule lets us find tangent lines without having to use the definition of the derivative. Okay, so we still need to know how to use the definition of the derivative, but going forward, we're not going to really use it to find derivatives. We're just going to use, for now, the power rule. So here's an example where I want to find the equation of the tangent line to the curve f of x equals x root x at the point 1, 1. So first thing I'm going to do, remember, finding the tangent line requires finding the slope and then finding the equation of the line. So the first thing I have to do is find the slope, which is the derivative at a particular point. So here's my function. Okay, it's not set up nice to use the power rule, so I can kind of rewrite this. So I can say that this is the same thing as saying x times x to the 1/2. So my function is really x to the 3/2. Okay, so I'm just rewriting it so I can use the power rule. So now I'm going to find the derivative. F prime of x is equal to 3/2, that comes down, x, and then 3/2 minus 1, so minus 2/2, so that gives us 1/2. So that's my derivative. Because I want to find the tangent line, I have to find the slope, and the slope is a number. So this is the equation to find the slope, but I'm using the point 1, 1, so that x value of 1 is what I'm going to plug in. So f prime at 1 is going to be 3/2 times 1 to the 1/2, which is 3/2. So this is the slope of the tangent line at the point 1, 1. And now I'm just going to use my point slope form, and I'm going to use this point and this slope. So y minus the y value of 1 equals the slope x minus the x value of 1. Okay, so you could leave it just like this. If you wanted to solve it for y, you can get y equals 3/2 x minus 1/2. Okay, either one is fine. Just finding the slope, plugging it into point slope form, and finding the equation. The constant multiple rule, basically this is just saying if you're taking the derivative of a function and you have a constant in front of it, you're using the power rule, but you're just going to multiply it to the number that's already in front. So you can split it up however you want. Easiest way, just literally multiply it in front. So if I have y equals 3x to the 4th, and I'm finding the derivative, y prime is equal to, I'm going to multiply the 4 down in front. So it's 4 times 3, so I get 12. X, the exponent is going to subtract 1. So 12x to the 3rd. And then there's the sum rule and the difference rule. Okay, basically that's just saying if you have multiple things that are being added and subtracted together, just take the derivative of each piece. So it's nothing super fancy. So if I wanted to find the derivative of this whole equation here, y prime equals, I'm just taking the derivative of every piece. So the derivative of x to the 8th would be 8x to the 7th. The derivative of 12x to the 5th would be 60x to the 4th. The derivative of 4x or negative 4x to the 4th would be negative 16x to the 3rd. The derivative of 10x cubed would be 30x x squared. The derivative of negative 6x would be negative 6. And then the derivative of 5 is just 0. So here is my derivative. Oops. Okay, so looking at a couple of other examples here, remember that your goal for now, because we don't know how to do any other type of derivative as of this moment, is to make it look like something that we can use the power rule for. So when I look at the first example, this h of t, it's not set up nice for the power rule because I have two things going on. So we're going to distribute. So I'm just going to say that this is the same thing as 10t to the third minus 12t. So now that I have it set up a little bit nicer, I can find the derivative easier. So h prime of t is going to be 30t squared minus 12. Okay, and then this example here, okay, even though we have a power, because it's not like x or 2x or whatever to the power, we have something that's being added. We have to actually write this twice and FOIL it out and expand it before we can do the power rule. So we're going to write it twice. So our p of x is really going to be 4x squared plus 4x plus 1. So now when I take the derivative of this, I'm going to get 8x plus 4. So you're making it easier for yourself to use the power rule. Okay, so another type of like application, I guess, type of example. So find the points on the curve y equals x to the fourth minus 6x squared plus 4, where the tangent line is horizontal. So instead of asking for the equation of the tangent line, it's asking for the points where the tangent line is horizontal. So horizontal tangent line, means that the slope is equal to 0. Right? If it's a horizontal tangent line, the slope is 0. So we want to find when is the slope 0. So we have to first find the equation for the slope, right, which is the derivative. So y prime, if I take the derivative of this, is going to give me 4x cubed minus 12x. That's my derivative. So that's the equation for the slope. I want to know when is this equal to 0. So I'm going to set it to 0. 4x cubed minus 12x equals 0. Okay, now we're just going to use algebra and we're going to factor. So I'm going to pull out a 4x and we have x squared minus 3 equals 0. If I set each thing to 0, I'm going to get x equals 0 from the 4x. X squared minus 3, if I solve it and set it to 0, I'm going to get that x is equal to positive root 3 and x is equal to negative root 3. Okay, so that's just basic algebra solving skills. So we have 3 different x values and we want to know the points. So that means we have to find the corresponding y values. So what I'm going to do is do y of 0. So I'm going to take the original y function, which is up here, and I'm going to plug in 0. And when I do that, I get 4. So one of my points is going to be 0, 4. I'm going to do y of positive root 3. So I'm going to plug in root 3 for my x's. When I do that, I get negative 5. So root 3 negative 5 is another point. And then I'm going to do y of negative root 3. And again, plug in negative root 3 for your x values, and you get negative 5. So my last point is negative root 3, negative 5. So these are the 3 points where the tangent line is going to be horizontal for that curve. The equation of motion of a particle is S equals that thing. Instead of S, sometimes they use x of t. And S is measured in centimeters and t is in seconds. We want to find the acceleration as a function of time and then find the acceleration after 2 seconds. So we're going to talk a lot more about motion later on, but the main idea is that you have x of t, which is the same thing as saying s. That's like your position. You have v of t, which is our velocity, and we have a of t, which is our acceleration. So basically, we're going to go from position to velocity by finding the derivative. And then we're going to go from velocity to acceleration by finding the derivative of the velocity. So we have the position. What we're going to do is find the velocity first. So the velocity is equal to the derivative of the position, which is here. So I'm going to find the derivative of this using the power rule. So 6t squared minus 10t plus 3. So that's the equation for the velocity. And now we have to find it for the acceleration. So acceleration is the derivative of velocity, which is the second derivative of the position. So we're taking the derivative of the velocity. So we get 12t minus 10. So it asked for find the acceleration as a function of time, which is this 12t minus 10. And then what is the acceleration after 2 seconds? So we're going to find a of 2. So all we're going to do is take our a function and plug 2 in. So 12 times 2 minus 10. And this is going to give us 14. And then our units for this, because the position is meters and the time is seconds, the velocity is the change in y over change in x, right? It's the slope. So it'd be meters per second. And the acceleration is going to be meters per second, since it's the change in the y value of the velocity over the x value. So we can say it's meters per second squared. And if this doesn't make 100% sense right this minute, we are going to talk a lot more about the position and velocity and acceleration. This is just a very little mini intro to that. And then the last thing we're going to talk about is the derivative of e to the x. If you're interested in why it is, I can send you some information about it. I had them on my slides and it was just, I think, too much because you don't really need to know why unless you're curious about it. But the derivative of e to the x is e to the x, which is so fun, so great, so easy, right? E to the x, e to the x. So here's my example. Find the derivative, the first derivative and the second derivative of e to the x minus x. So first derivative, so f prime of x, I'm going to take the derivative of each piece. So the derivative of e to the x is e to the x. The derivative of negative x is negative 1. There's my first derivative. Oops, as I cross it out. Okay. Second derivative, I'm taking the derivative of the first derivative. So the derivative of e to the x is e to the x. Derivative of negative 1 is 0. So my second derivative is e to the x. Pretty simple.